Good afternoon, ladies and gentlemen, and welcome to the Citation 10 Engineering Briefing. This is the briefing that I've been anxious to give. The past few years, we've provided a lot of information about what the Citation 10 was going to be. This year, we can tell you a lot about how it flies. Prior to the first flight crew had flown the in-flight simulator at CalSpan with the stability derivatives from the Citation 10 wind tunnel tests. They had flown our own Iron Bird with the computer simulation tied to our hydraulic system. All of the functional tests had been run, and the taxi tests had been completed, including several high-speed runs where the crew was able to get the airplane just clear of the runway and actually feel the controllability. On the 21st of December in late afternoon, with Doug Hazelwood and Ken Kimball at the controls, the Citation 10 prototype took to the air for the very first time. The takeoff and climb out were beautiful. I might mention we always leave the airplane in the takeoff configuration during a first flight until we have some altitude and the chase plane is in position. After a good look from the chase airplane and the airplane is handling as anticipated, then the landing gear is retracted. Another look is taken at the airplane from the chase, and the flaps are retracted for the clean maneuvering tests. When all of the handling checks were completed, the airplane was configured for landing. Doug said the airplane handled really nice for the approach and the landing. The touchdown, well, the next one was even better. I know that everyone always says the first flight is a great success, but in fact, this first flight was a great success. Following a series of flights, the airplane was painted. Then ground vibration tests were conducted to prepare the airplane for expansion of the airspeed, Mach, and altitude envelope. These ground vibration tests are conducted with the airplane suspended in a manner to simulate the airplane as close as possible to being airborne. We go to great lengths to achieve a soft mounting of the total airplane. You can probably see that these large rubber bladders underneath the wheel. The vibration characteristics are determined over the entire airplane. A complete frequency spectrum is excited with the large shakers, and the modal response is recorded. These tests are correlated then with the high-speed flutter model results obtained from the NASA Langley transonic flutter tunnel and our own flutter analysis. This is the flutter model in the test cell that you see here at undergoing tests at Langley. I know many of you were present on January the 17th of this year when we had the ceremonial first flight of the prototype. This gave us an opportunity for the airplane to be viewed. Since the actual first flight occurred just prior to the holidays and with the uncertainty of having weather conditions good enough for an actual first flight, this worked out to be the better way for our guests as well as ourselves, we believe. This was an exciting day for all of the people who worked around the clock to bring the Citation 10 to the first stage of flight testing. With the data correlated from the ground vibration tests, the flutter model, and the flutter analysis, the envelope expansion was underway. We brought in a T-38 for the chase plane since no commercial airplane would be able to stay with the Citation 10 even through this first phase of the altitude and Mach envelope expansion. You might be interested in knowing how we do the envelope expansion. The in-flight flutter testing is accomplished with a computer-controlled shaker system with shakers in the wingtips and in the horizontal tail. This enables us to excite the exact frequencies we need to excite and determine the damping online. This data is telemetered to our flutter engineering team, where each point is analyzed prior to proceeding to the next speed and/or altitude. The team is able to accurately and safely expand the envelope really quite quickly this way. Phase 1 of this testing was executed exactly as planned through Mach 0.93, well beyond our planned red line Mach. As we proceeded through the test points, We were also carefully evaluating the stability and controllability at these high Mach numbers. Here is where we had an incredibly delightful surprise. We could feel no Mach-induced separation. By that I mean at high Mach numbers, we fully expected to have local areas where the shock waves would cause separation of the airflow that we would have to track down and correct, but we found none. The other piece of this surprise was that even though the wind tunnel had shown that we would have good stability and control, it also showed that we would need considerable Mach trim compensation. So far, it looks like we will need very little Mach compensation. The high altitude, high Mach testing confirmed that we would need full-time yaw damping, just as our analysis had shown. As a result of this confirmation and the requirement to comply with the latest regulations, and more significantly, some very recent interpretations by the FAA concerning reliability and jam controls, we have changed the rudder design to a split rudder configuration. You may be able to see it here. The upper rudder segment is electrically driven with redundant systems, and the lower segment is hydraulically driven with redundant systems. This will give us assurance of always having full-time yaw damping and should enable us to dispatch with a channel out on either the upper or lower segment. We next started making preparation for the stall speed and stall characteristics testing. We installed ballistically deployed spin chutes in the stinger to provide safety in case we encounter the unexpected during the stall investigation testing. This is where we had our second pleasant surprise. Normally, the stall investigation and tailoring phase is a rather lengthy series of flights. The Citation 10 turned out to need very little tailoring. The slats result in good natural characteristics with any combination of flaps, center gravity, entry conditions, in other words, rate of airspeed reduction or attitudes. We fully expected to have to use a stall barrier system to inhibit the stall. We have now established that this will not be necessary. Anytime the airplane approaches a clean stall, the slats will be automatically deployed, which results in excellent stall characteristics. This particular series was with the slats retracted. You can see the yarn tufts as the stall progresses along the wing. Rick Trussell is flying the stalls. Rick is the project pilot and has done most of the prototype flying. The prototype was completed prior to final definition of the wing to fuselage fairing. The original fairing produced a shock wave right across the wheel well area as a result of accelerating the air too quickly. We have now installed the final fairing, which we optimized in the high-speed tunnel, and that's the fairing that you see here. This eliminated the shock drag at the high cruise Mach numbers as we expected. By the way, this shot isn't an animation. This is really some nice in-flight photography. We have now completed a series of very precise speed tests with the airspeed system calibrated from the T-38 Pace airplane. We have now confirmed that the Citation 10 will, in fact, cruise at Mach 0.90. Of course, the engine is a vital part of the performance of the Citation 10, as well as the aerodynamics. The Allison engines have performed flawlessly throughout the testing. One of the first comments made by people watching the first flight was how quiet the airplane was on takeoff. The high bypass ratio and the forced mixer in the exhaust are the basic reasons for this exceptionally low noise signature. All of the demanding, maybe I should say grueling, certification tests were completed at Allison on the engine this year. I thought you might be interested in seeing some of these tests. The first one is a blade off test where the fan blade is blown off with a charge and the engine is shown to keep the blade from getting out the side of the engine. It's pretty spectacular, isn't it? They have also completed the ice tests where sheets of ice are ingested, and then also the ice balls or the hailstones, where the engine is subjected to these large chunks of ice and then shown to still be producing engine thrust. We've conducted extensive tests at Cessna on the engine test bed to define the inlet characteristics, to optimize the air start envelope, and to tune the engine handling. The engine, as you probably know, uses dual FADEC controls, which gives a much better control of the engines than anything you can imagine. The FADEC controls N1 directly. It sets takeoff thrust exactly and maintains the correct power setting for the full climb out to cruise altitude regardless of temperature. Allison has conducted exhaustive testing required by the most recent, and I should say demanding, regulations to assure reliability and fail-safe operation of the controls. This includes testing to assure HRF and Lightning do not produce a problem, and Cessna has also conducted tests to provide our own independent assurance. Much of the development testing has been to produce the control harmony that we think would be the most desirable in both roll and pitch while still protecting the opportunity to fly the airplane on manual reversion. Extensive systems testing under all conditions of altitude, speed, and maneuvering flight have been conducted, including simulated asymmetric conditions. The other very important aspect of the systems testing has been the reliability testing to assure low failure rates and high dispatchability. Our hydraulic and control system, Iron Bird, has been and is still proving to be invaluable in this regard. We have assigned one of our key people to this task. His assignment is very simple. Do what is necessary to assure that the Citation 10 goes to the first customers without systems problems. Citation 7 uses a PPG glass electrical windshield, which is a patented surface which causes the rain to bead up and flow off even better than on a stretched acrylic windshield. This has proven to be very effective on the Citation 7 and is being used on the Citation 10 as well. A recent improvement to the windshield surface has been introduced, which greatly improves the resistance to static discharge and consequently extends the life of the rain clearing quality. I noticed recently that Boeing is using this same surface on the 777, and they are planning to use it on all of their models eventually. We are experimenting with the use of an electric blower in lieu of using the bleed air to clear the windshield in the low-speed taxi case. Nothing is needed to augment the natural characteristics except when you're sitting on the ground or just low-speed taxi. The blower does look promising so far. Thrust reverser testing has been completed to show the trajectory of the plume. I thought it might be interesting for you to see how we inject smoke, as shown here in these runs, to be able to visualize the effect from the onboard cameras and also from the ground-based cameras. This helps us to analyze the controllability during thrust reverser operation and to determine at what speed re-ingestion of the exhaust starts to occur, that is, where it starts to come back into the inlet. This tells us where to set the cutoff speed. Testing has also been completed to establish that water from the nose tires is not ingested by the engines. We begin at low speeds here, about 60 knots, and then build up to about 120 knots. The result was that we had water getting close to the inlet at 80 knots, and then it continued to improve as the speed increased. We have constructed a new facility for testing of the fuel system. This is the fuel Iron Bird with the Citation 10 wing and fuel system installed. Actually, it's half of a wing and the center section. We have the capability to exercise the fueling and defueling, but its primary value is in testing fuel transfer and the fuel boost system as the engines are supplied with fuel. As you can see, we can produce not only normal but some pretty exaggerated attitudes as well. We can actually do a lot of the certification testing in the Iron Bird instead of using the airplane. We have been extremely busy this past year completing the developmental structural testing and defining the final production airframe configuration. We completed over 80,000 flights of the wing and wing carry-through in this fatigue test setup. This resulted in refinement of the various structural elements, and these have all been incorporated in the first production airplane. Fatigue testing of the composite aft pressure bulkhead, that is behind the baggage compartment, is tested in a high humidity, high temperature environmental chamber, as really all of our composite structural members are. These fatigue tests resulted in a failure from damage which we inflicted. After we had 48,000 flights on the bulkhead and had no failures, we inflicted a 2.5-inch crosshair saw cut and continued to cycle the article. This is when we got the failure. We then made a design change and have retested the bulkhead and established that it will not only be a durable but a very tolerant bulkhead to damage. We also have a pressure bulkhead between the cabin and the baggage compartment, which is fully qualified to 51,000 feet. Any loss in baggage compartment would not cause a loss in cabin pressure. Structural certification testing is well underway. The pressure vessel has to withstand a pressure of 25 psi to comply with the 51,000-foot requirements. On the first test of the full cabin, we passed the required 25 psi in the water tank. When we examined the article, though, we found some distress in the nose wheel area. We modified the design and then retested to be sure that the change was effective. Proof testing of the wing was completed on this development article to 100% of limit load in upbending and 100% in downbending. All of the structure has been completed to at least limit load and some to ultimate load, which is 150%. The final static ultimate strength article has the production configuration incorporated and is undergoing preparation for certification strength tests at this time. These tests turn out to be very low risk after we've completed the Nastran analysis and completed this development testing. The landing gear structural dynamic testing has been accomplished. The main gear and nose gear were defined analytically and tuned analytically. The drop testing was then run in the large drop tower to correlate and confirm the results of the analytical model. This is the nose gear shown in the drop tower, but the main gears also completed a series of drops. The airplane taxi is very smooth. You can make a good touchdown easily and consistently with the trailing link main gear. I know all of you would be disappointed if you did not get to see at least one birdshot event, so I've included this sequence of a horizontal stabilizer being impacted with an 8-pound bird during developmental testing. As you can see, the structure took the big bird quite well. A lot of attention has been devoted to the development of the symbology of the primary flight display. The most extensive effort has been to achieve what we believe to be the very best in vertical air data displays, airspeed, altitude especially. Honeywell and Cessna, together with participation from our advisory council members, have greatly improved the readability as well as what I refer to as incidental awareness by optimizing the use of trend vectors, color changes, and large indices or carets. We have also improved the integration of the attitude information and computed flight guidance information with the vertical air data and the angle of attack fast-slow information. As opinionated as we all are as pilots, I really think you will be impressed. If not impressed, at least pleased. ICAS provides a tremendous opportunity to present more information than anyone could possibly use. The task has been twofold. First, to assure that we present the information that the pilot really needs to have and in the right sequence, then to eliminate the information that he would be unable to cope with. This has been a most intense task. We have a page for normal takeoff sequence, a page for the normal climb cruise portion of the flight where the display is decluttered, we say, and then a page for the approach phase. There are then displays to allow viewing and analyzing various systems. The system's information can be displayed in larger format on the MFD as well as on the ICAS tube. We believe we have an excellent result, but I'm sure that the ICAS display is going to be an area where we have continuing opportunity for improvement and continuing discussion about which way is the best way. We will be offering a performance computer from Honeywell, which is integrated with the rest of the Honeywell flight guidance system and provides all of the functions which we believe you would want. We got excellent guidance from our advisory council in the selection of the features for this system. The system is referred to as SmartPerf, and it's named SmartPerf because the intelligence in the computer is updated with each flight automatically so that it represents the actual performance of the airplane the way you fly it. It has full capability for all phases of flight, the takeoff, climb, cruise, descent, and it also includes a what-if capability. A new radar from Honeywell will be a part of the basic configuration and will provide improved resolution along with a long-life magnetron and other higher reliability components. TCAS 2 will be available. We fully integrated into the basic system. Ground proximity warning will also be available with some improved systems coming out of Allied Signal. Citation 10 systems include features which will make it easier to diagnose problems and maintain the aircraft than any other business jet. To begin with, the Primus 2000 system includes the Integrated Maintenance Test, or IMT, feature. The system is extremely useful, especially when troubleshooting intermittent faults. For ground maintenance, the IMT will present diagnostic information on a cockpit display. This information can also be downloaded to a disk for evaluation off of the airplane. Primary systems, as shown on the screen, are monitored by IMT. The subsystems supported by IMT contain non-volatile memory for fault storage. Notice that the radio package is served by its own IMT. A typical display, if a fault is encountered, could be shown on the screen on the ICAS as seen here. Other aircraft systems integrated with the Primus 2000 IMT system include the engine FADEC, the APU control, fuel quantity, and the door latch system. Other systems such as the cabin pressurization and temperature control, just to name a couple, have dedicated byte readout. The design is directed toward a diagnostic and a maintenance system which will quickly return the aircraft to service if a fault is encountered. Production engineering for the Citation 10 is all released. Production line flow began the first week in June, and the jigs used to produce the test articles are moving from engineering to the production line as required to phase with the production line flow. The wing and fuselage jigs have all been transferred and only a few small jigs remain in engineering. The precision of the assembly has proven to be the best ever, even better than we had with the Citation Jet. This is attributed to the additional utilization of CATIA, which improves the three-dimensional characteristics of the design over CADM. We expect to have an extremely smooth transition to production. We had as many as 50 people from the production line involved in the construction of the prototype and the first production airplanes in engineering. These people are now phasing into the production line, carrying that experience and knowledge with them. A second production airplane is being completed in engineering, again with production and experimental people working together, and will fly before the end of this year. Certification will be completed before we meet at NBAA again next year if all goes well. And I have to tell you that integrated engineering does work. I'd like to wrap up today by telling you about very recent flight test activity. After bringing the prototype up to configuration for full envelope expansion, we have completed the dive controllability and the flutter testing. We have expanded the envelope to 51,000 feet and accomplished emergency descents down to 14,000 feet. As many of you may remember, we designed the Model 650 to assure that we could descend in less than 4 minutes to prevent injury to passengers in the very, very unlikely case that pressurization was lost and then someone failed to get an oxygen mask on. The 750 has now demonstrated the ability to also meet this criteria. We also incorporated an emergency descent mode in the autopilot, just as we have in the Model 650, to aid in executing the emergency descent quickly and with maximum accuracy. The dive testing has been conducted out to a true Mach number of 0.98. There was no Mach tuck or controllability problem of any kind. At Mach 0.98, there's not much of any of the airplane that's not supersonic. It looks very much like we'll be able to clear the airplane for an MMO of 0.91 or 0.92. We've also completed the flutter testing through the dive speed requirement of 405 knots, which clears the airplane to the planned VMO of 350 knots. On September the 15th, 1993, the Citation X prototype was rolled out of the experimental hangar. 1 year later to the day, September the 15th of this year, the first production airplane was rolled out of the hangar. This is the actual first flight of the production airplane, which occurred only 12 days after rollout. This airplane, as well as the one to follow, will be extensively used in the certification program, primarily for aircraft systems. You saw this airplane in formation with the prototype in the flyover just a little earlier. On the flight from Wichita, the airplane took off just under gross weight and cruised at 41,000 feet, initially at Mach 0.89, and was at Mach 0.90 for much of the flight. We covered the 900 nautical miles in 1 hour and 58 minutes and burned only 4,800 pounds of fuel. We are really pleased for you to be able to examine the Citation X prototype here today. The production airplane returned to Wichita to keep the test program moving. We will be taking the prototype to New Orleans, where it will also be available for others to see there. Incidentally, and perhaps notably, the rollout of the production Citation X occurred on the silver anniversary of the first flight of the original Citation. We have come from a 0.6 Mach cruise to a 0.9 Mach cruise, and from a 35,000 foot maximum altitude to a 51,000 foot altitude, and from a 1,200 nautical mile range to a 3,300 nautical mile range, and we cover most points in between with our current line of citations. One thing, however, has not changed and will not change, and that is our commitment to provide the safest, most dependable, and most usable corporate aircraft for your needs. Thank you very much for being here and for sharing in this event with all of us from Cessna.